So we showed last week this 3D model of cyclohexane. Despite looking flat from the top, when you put it on its side, it actually looks like this. It just looks like a zigzag. But this is not incredibly useful for us because, as you know, there's one carbon on either end, but then there's actually a carbon in back and in front on these vertexes. So we need to take this structure that we saw and we need to tilt it onto its side. That means that I'm going to get these two lines in the middle that are parallel to each other. And it's going to help me as well if I can offset them. So I'm going to draw them with this second one kind of lagging halfway behind. Then I can connect them down to this one point. Now, here's how I like to show this. And by the way, we can draw this out, drawing a chair. These are the steps that I follow. One, draw two parallel lines that are offset. One of them is lagging behind the other. You could also draw this like this. Whichever one is on bottom is lagging behind. Yeah? Step two is to connect those lines, just like we're seeing here, connect them to a point on either side. So on the line that's pointing down, you're going to have two new lines coming to meet this. So I call that, on the down side, place an up V. So it kind of looks like a V, right? And now on the upside, connect them by a down V. And then we can do the same thing from our other perspective. Have our arrows, have our parallel lines slanted upwards, and then connect the upward pointing side with the down V, the downward pointing side with an up V. What we've done is drawn a chair. This is not an effective way to draw a chair because it hides two of our atoms in the back. So instead, we tilt it onto its side and we draw it like this. Let me pull up that same website that I showed you guys last week. Because, believe it or not, we have some more assumed perspective here. Do you remember the applications I told you we used assumed perspective last week? When did I talk about that? That's the website. Oh, okay. I'm going to go to SimOtter. But when we talked about having some assumed perspective, what context were we talking about? Oh, yeah. Our projections. The Newman projections have an assumed perspective. You're sighted down a bond. And then there's actually things that are coming towards you and away from you, but we just call them flat. The sawhorse had an assumed projection. Round of applause. Thank you, Peter. This is going to save you guys the headache of having to draw out some of these. And you get it on double-sided.
Yeah, I printed out some and one-sided.
So you get twice as much to do. Is that all of them? Is that more?
Yeah,
those are one-sided? Yeah. Oh. I guess it doesn't matter if you have one-sided or two. Maybe I'll save those for next lesson. You're welcome. So we had some assumed perspective when we were looking at sawhorse projections and when we were looking at Fisher projections. and when we were looking at Newman projections. We're going to have some more assumed perspective in our chairs. So here's that top-down view. It's not really flat. We twist it onto its side, and we don't want to just see this zigzag structure, so we offset it. And we offset it like this. Here are those two lines, parallel but offset. Going up, they're connected by a down V. Going down, they're connected by an up V. This is what we're sketching. Which part of that ring, the flat chair, is closer to you? This top part or this bottom part? Good. Assumed perspective. We're not going to show that every time, although you can. You can assume this perspective. The front is shaded, and the back is not. So we can bold those front lines to show that they are coming towards us. And not really to say that they're coming towards us, but just that they lie closer to us. But it gets really tedious to draw that on the bottom every time. So we're going to assume that. The bottom of the ring is what's closest to us. Are you guys okay assuming that? Okay. How do you feel on your rings, on your chairs? Do they look good? Because mine never looked good until I had to teach it, and then they got better. One thing that I try to do in my class is not grade you on how well you can draw a chair. I did that. It's never pretty. Sometimes it's pretty, but usually it's just not pretty. So you will need to know how to interpret a chair, and I recommend that you know how to draw one because it will make things a lot easier for you. But you certainly need to be able to have this perspective on it. Okay. So let's look at the energy of chair conformations. First, I want to look at what if there is just one substituent. A mono-substituted chair. Anybody want to give me a substituent? What's a group that you could have coming off of your ring? An alcohol, an OH. So let's look at cyclohexanol. And let's try to decide, are its two chair conformations equal in energy, or does one of them lie higher in energy than the other? Deal? That's what we'll try to answer. Is one of them higher in energy, or are they both equal? Because as it turns out, cyclohexane, two equal energy chair conformations with some energy needed to get between them. Similar to how with your Newman projections, you can get to two equal energy Newman projections, but you need to go through a high energy eclipse. Here you need to go through a high energy boat. Then you can come down to the next one. If it's just cyclohexane, it's all the same energy. So let's draw its two chair conformations. Here's the deal. I think you guys can see that you can draw the chair pointed in either direction. I have the perspective of this 3D model so that it resembles the chair on the right. But all it takes is a small rotation before I have the model that's on the left, where these parallel lines are going up to the right. It does not matter which you use, but sometimes active requires you to show the other version when submitting the second chair conformation. And we actually call this conversion, this transformation, from one chair to the next, we call it a chair flip. Because we are going to flip some of those groups and where they are in the chair, and so we're flipping chair conformations. So I can draw this any way that I want to, and I can draw the second one any way that I want to, but it turns out that I will just need to be specific about where to place things. But active will tell you you need to draw this specifically pointed the other direction in order for it to count. So we'll show it on the other direction, but I'll show you in a little bit why this is not so important. All right. So let's say that I've got cyclohexanol, and let's just pretend here that the blue is my alcohol. I'm covering up these red spots for now because we'll use them in a little bit. Does it matter which carbon I draw it on in my chair, the OH? No, it does not. It doesn't matter. So anybody want to pick one? Left, right, back, left. What do you think? Front, center, that doesn't exist. Front left or front right? Here? Okay. So I want you to notice that that doesn't line up with what I have on the board right now. So I'm going to make that line up with what I have on the board. I'm going to rotate this so that my parallel lines are slanted upwards. Do you see it? Here's that carbon you wanted. Was it you, Jackie? Okay. Here's the alcohol. It can have one of two positions. From this carbon, it can either go straight up or it can actually come out towards you and slant it down a little bit. Based on the information that we have, what position is the OH in? We don't know. We don't have that kind of information. All we know is that it's on that carbon. But we don't have a wedge or a dash to give us any sort of physical observation. So let's change that, shall we? An easy modification. Any of you can do this. Take your stick going to the OH and make it a wedge. Now, if that's really a wedge, and we're looking at the top-down structure, wedge means it's coming towards you. And this is the carbon we want the OH to be on. Granted, it's just rotated around a little bit. That means it's coming towards you. So keep your eye on this dot. What position does it end up taking? The top. So here's some terminology that we can use. These up groups, things that are wedged, we'll call them up. Things that are dashed, call them down. We don't have any dashes right now. So we don't have any down groups on cyclohexanol. We just have the up OH. I guess you could say we have the down hydrogen that's connected. So this up OH, it shows up on this carbon like this, which is different than the OH, which looks like this. There is a tip for drawing the OH, for drawing the H, which is that its line should actually be parallel to these two lines. If you've done that right, then you've drawn it. I don't know that mine looks exactly parallel, but it can be really challenging to actually make it look good anyway. So I'm giving myself a little break there. That's one chair conformation. Now, as you guys were hopefully feeling out earlier, in a chair flip, anything that's pointing straight up or straight down is going to change its position. One way that you can do this with a model is to take hold of the 1, 3, 5 positions and change all of them, and then take the 2, 4, 6 positions and change them. The positions 1, 3, and 5 alternating every other, they all have the same orientation. And those positions 2, 4, and 6 all have the same orientation. So you're going to take one of these carbons that has a group that's pointing straight up, and you're going to twist it in such a way that now that group is pointing, not that group, sorry. Now that carbon has a group that's pointing straight down. So remember earlier I said we're going to use this blue dot to represent our alcohol in this example. And we said that it's pointing straight up. When it goes through this flip, where is it pointing? Is it pointing straight down? The OH group, the blue group? Is it pointing straight up? How can you describe its orientation? A little bit up. It's almost like it's even with the equator of the ring. So we named two positions here where it's pointing straight up. We call that up axial. After a chair flip, this OH is no longer on one of these carbons that is sat pointed up, but it's now on a carbon that is sat pointed down. And it doesn't matter inherently which one I choose, but if I choose this carbon here, that OH is still pointing up. It's just not pointing up axial to the ring. It's now pointing up equatorial to the ring. These are the terms we'll use to describe substituents on the ring. You okay with that? What do you notice about the description the OH group has in both chairs? It's up, axial, and it's up, equatorial. And it's up in this top-down view of the structure. Cardi B had it right when she said, if it's up, then it's up, then it's up, then it's stuck. If your group is up, it can move between axial and equatorial, but it will always stay pointed slightly up. So, some other terms that we have then. How could we describe this hydrogen? Is it up? It's down. Is it axial? It's equatorial at the moment because the other group attached to that carbon is axial. What does the hydrogen become in the second chair? Down axial, pointing straight down on that carbon. During a chair flip, every up group stays up, every down group stays down. Every axial group becomes equatorial, every equatorial group becomes axial. Now we can try to describe the carbons in a similar way. We can come in and say the carbon that our alcohol is on is defined by its axial group. Or if you look at this, it's literally split into two groups. There are those carbons that are up, and there are those carbons that are down relative to this plane of the ring. But the ring is not in a plane, right? So if you put a plane through this, you can set it into two groups. 3 up carbons, 3 down carbons, aligning with their axial groups. So this carbon that the OH started as an up carbon. Why? Because it has an up axial group. That carbon is quite literally oriented up in space. Vertex is pointing up to it. What happened to that carbon during the ring flip? It became a down carbon. This is why its up axial group transformed to up equatorial. And its down equatorial group transformed to down axial because it is now a down carbon. So you have to be careful thinking about the terminology. Describe carbons separate from how you would describe their substituents. Every carbon has 2 groups, axial and equatorial. A down carbon always has a down axial group and an up equatorial group. An up carbon always has anybody? An up axial group and a down equatorial group. So during a chair flip, up carbons become down carbons, and vice versa. Sorry, I don't know how to spell vice. Yeah? That's what this process is, of taking 1, 3, 5 and flipping them so that their orientation in space is now changed. That is the conformational change. Every up group becomes what? An up group. And down groups stay down groups. But axial becomes equatorial, and vice versa.
It's a C, not an S on the vice.
Oh, is that the only thing I'm doing wrong? Thank you. It's Latin anyways, isn't it?
I think so.
It's dead. I can rename it. Okay, so we have drawn the 2 chairs of cyclohexanol, but we haven't actually decided which of them is higher energy. And by the way, I mentioned, so I'm going to redraw them. I mentioned that you don't have to draw the other chair to predict the other chair conformation. You don't need the chairs to be angled differently. Active will require that you do, but you can actually draw this exact same structure. Notice how they're angled the same way. All you have to do is ensure that every carbon that was an up carbon is now a down carbon. And whichever direction you rotate, if you rotate all of your carbons clockwise, rotate them all clockwise. If you rotate any of them counterclockwise, rotate them counterclockwise. So here, I'll continue rotating counterclockwise. I go to a down carbon, and I get this up axial OH. Okay? So which of them is higher energy? Well, we can actually use Newman projections to try and prove it. I can give you the rules, and the rules will make this a lot easier than drawing Newman projections, but the Newman projections are kind of the proof. So here's how I'm going to do it. I want to get those substituents, the OH substituents, onto one of the carbons of a Newman projection. So I'm going to sight down this bond, and I'm going to do it from this direction. And then I'm going to sight down this bond from this direction. But unlike linear chains, when you sight down the bond of a Newman projection, when you sight down the bond of a chair, just want to get this guy flat for you. Every time I move it, it moves the wrong way. When you sight down the bonds in a chair, I'm afraid it's just going to have to be crooked. Here's a dot, here's a circle, here's another dot, and another circle. It is actually two Newman projections that you will see. If you sight down this bond, you're also sighting down this parallel bond behind it. If you sight down this bond, you are also sighting down this parallel bond behind it. So the Newman projection of a chair is two Newman projections together in a trench coat. So you can start your cartoon off by drawing two big cartoon eyes, and we're going to connect them to each other. You can see here how the front carbons are connected by this CH2 group, and you can see how these back carbons are connected by a CH2 group. So it's all going to connect in the center. We just want to make sure that our substituent ends up on the front or back carbons and not on these CH2 groups in the middle. But we did that. Is the OH on the right-hand Newman projection or the left? It's on the right hand, because remember, this bottom part of the ring is closer to you, so you pull that out, smack it on the right. Is the OH on the front carbon or the back carbon of the Newman projection? Why is it back? Because I'm starting here.
Oh, yes.
And I'm looking this way.
I was looking.
There you go. Put your head in the plane of the board. All right. Here's my front carbon on the right. Here's my front carbon on the left. How are they connected? They're connected by a, or an up carbon, correct? Do you notice how that group is literally pointing up? So I can start my Newman projection by taking the front carbons of each and connecting them by an up carbon. Chairs. Are they more closely related to the eclipsed Newman projection or the staggered Newman projection? Staggered. Which means now that I have these little markers, I can start filling out the rest of that front Newman projection. It's still going to have that little peace sign, that little Y, showing the three groups coming off. Now that I know it's the orientation of one of them, I can figure out the other. On the back carbons, how are they connected? By an up carbon or a down carbon? A down carbon. So I can connect the back carbons by this down group. And again, I can fill in the rest of the Newman projections. That's essentially what we're looking at here. The only distinction is that the orientation that I have here is flipped, where the front carbons are connected by a down and the back carbons are connected by an up. But that's what we're looking at, is this diagram of the chair. Where does my OH go? Well, we said before, it's on the right-hand side, because I'm looking at this, and it's on the back carbon. The back carbon has up, down, and then this CH2. What am I allowed? Where does it go? It goes up, because it's up axial. In fact, this Newman projection should help you see better the up axial, down equatorial, down axial, up equatorial positions. All right, now let's look at my chair flip. Oh, sorry, I want to come in and just say that the rest of these groups are all hydrogens, by the way. Can't leave them blank, because if we leave them blank, then that means they're all CH3 groups. Let's look at the chair conformation on the right. What are the front carbons connected by? An up carbon. And the back carbons must then be connected by a down carbon. And I can fill in the rest of the structure of my Newman projection. Staggered. Staggered. However you guys say. Where is the OH now? Is it on the right-hand Newman projection or the left? It's still on the right. In fact, this one is a little bit easier, correct, Aiden? Because you are actually looking through the plane of the board for this one. Is it on the front carbon on the right or the back carbon on the right? And then just to be sure, we said that it should have what type of description on that carbon? Up equatorial. Is the front carbon, does the front carbon have an up equatorial position? Yes, it's this right here. Here's my OH. And then everything else, just hydrogens. Okay, take a minute, work with the people around you, use the prior knowledge you have on Newman projections to determine which of those two conformations has higher energy. Correct. Yeah. Up, up, up. Down, down, down. Good. That. We found that rotating around a sigma bond changes the energy. Even just a 60-degree rotation changes the energy. It does need energy to rotate, but who's to say that one energy won't be lower than the other? Maybe they'll be equal, but there could be a lower energy and a higher energy state. Well, is there just hydrogen around it? Oh, sorry, I noticed something.
So are we saying, even though it's on, even though it's in the back, is it still
Yeah, you think there's ghost travel? Which one?
I think the blue one on the left is.
Okay.
There you go.
I feel like that sounds right.
Yeah, we see it right now. Yeah, that's what I was saying. Yeah. So the OH is kind of just all out.
That's the bottom that you guys
Yeah. That's what I was gonna say, isn't it? Like, is it because this one's all the way out here, this one's just here?
Sarah, do you agree? How did we look for strain in our Newman projections? The front and the back carbons need to have non-hydrogen groups that are gauche to each other. Are there any non-hydrogen groups that are gauche to each other? But is it the same amount on both of them? There was a term I didn't teach you last week, and it kind of is a partner term to gauche. We said that gauche was two groups, one on the front, one on the back carbon, that are just offset next to each other. And I gave that analogy of being squished in an airplane seat. That's gauche. The other term is anti, which is literally two groups on opposite carbons that are just 180 degrees from each other. They're just pointed opposite. In fact, if you have a wedged and a dashed group on separate carbons, then those will be anti, because we notice that being wedged puts you on one side of a Newman projection, and being dashed puts you on the other. So anti-groups are wedged and dashed, or sometimes anti-groups are the in-plane groups. Like on a normal zigzag, when you look down a Newman projection, these lines that are in plane are anti to each other. That's their lowest energy, is when they're as far away as possible from each other. Once you get zig-zig, then that's an eclipsed conformation anyways, and that's always very high. But applying those terms here, if we look at the OH group, the only thing adjacent to it are hydrogens, no energy strain. And then there's a CH2 group that is anti to it on the ring in the conformation on the right. But the conformation on the left has the OH group and the CH2 group gauche to each other. And that is steric strain. It tricked you because the CH2 was written as a bond line. But those are two non-H groups next to each other. So here's what I want you to get from that. Axial groups, regardless of what they are, will always have steric strain with the other carbons in the ring. You guys agree that this CH2 we're looking at is this? It is. This OH has steric interactions with this CH2. Do you think that the OH only has steric interaction with that CH2? Or do you think that it also might have steric interactions with this other CH2? And we just can't see it because we're sighting down one of the bonds that carbon has. So if we took a different Newman projection, we could actually show how this OH group has the steric strain here. It would be challenging for us to show one Newman projection that shows both steric strains. So here's the rule. In chairs, axial groups have a minimum of 2 steric strains. Equatorial groups can have steric strain, just not in a mono-substituted structure like this. Because in a mono-substituted structure, you just got that one group moving around. But when you get di, tri, tetra, etc., you start getting the potential for more steric strain. So it's true that all axial groups have a minimum of 2 steric strains, but to minimize energy, minimize axial, and maximize equatorial groups, to have a lower energy, greater stability conformation. Are these two chairs equal in energy? No. Which chair is preferred? Which chair does the ring take on more times than not? The more stable chair. That's where it's fallen into this energy well. It takes a lot of energy to get up and over, but once you're up and over, it doesn't take a lot of energy to get back down. So it prefers, it's more statistically likely that it sits in this lower energy position until you heat it and get it moving. Okay? All you have to do when you start getting past mono-substituted is literally just count the number of axial groups. But what if there's a tie? What if there are two chair conformations that have the same number of groups, axial and equatorial, between them? This might be one of the structures I actually gave you. Let me give you something a little bit different. I'm still going to use terbutyl. How many axial groups here? How many axial substituents? 1. The terbutyl is axial. The OH is equatorial. How many, let me write this down. Axial, 1 equatorial. How many in the other chair? How many axial groups? It's the same. Because this axial group is going to become equatorial, and this equatorial group will become axial. So it's the same. I don't even have to draw it to know how many will be axial, how many will be equatorial. Which of them is the higher energy conformation? Or are they equal? Well, these are different groups, terbutyl and hydroxyl. And the same thing goes here in chairs. Increasing sterics, increasing strain. When I say sterics, I mean size. The more space it takes up, the more strain there is. So we know that terbutyl will make more strain than hydroxyl. So am I looking at the highest energy conformation, or am I looking at the lower energy conformation? Both conformations have the same number of axial and equatorial groups. So I can't just count the form with more axial. I have to decide which one makes up more strain, and then put that axial to have the highest energy or the least stable conformation. What do I have here? Highest energy, least stable. The other one that I haven't drawn is lower energy, more stable. And I can say that because I know that the change will just be swapping the terbutyl and the OH. And since terbutyl is already axial, it's already the highest energy. Okay, in front of you, you have this worksheet that I have uploaded onto our modules. I'll show you where to find it. Underneath Unit 2, Learning Objectives, Chairs and Absolute Configurations. We're just going to work on the chairs for right now. Here's what I want you to do. On that first structure, I have given you a di-substituted cyclohexane, and I've shown you one of its chair conformations, a wedge and a dashed OH. I want you to draw the second chair conformation. I'm giving you this hint about how you can change the perspective, and it's the exact same thing. I'm setting you up with that because when you do homework problems and your friends are doing homework problems, you might shift your perspective a little bit and still get the same structure, just looking at it from a different angle. So I want you to familiarize yourself with that. Draw the product, or draw the second chair conformation from two perspectives. They're exactly the same. That's why they're related by an equal sign. And I didn't do this consistently, sorry. There's this equilibrium sign between the chairs. That's because it does require energy to move between them. They're not resonance forms. They take energy to transition. That would be true between the other two sets below. What I want you to do on the second set is draw the two chair conformations. On the third set, I want you to draw the other chair conformation and the top-down view, including wedges and dashes of the groups. And for all three of these sets, circle the more stable conformer. Go ahead and get started on this. We're going to save that last part for later in our lecture, by the way. You've got this anyway, so you didn't need that. So what did I do? Because the blueprint was telling me load ink and load paper, and both trays had paper, and I just couldn't get it to. What do they call that? Sadism? They're sadistic. Where's it masochistic? I hear you. Yeah, that would raise the conspiracy theorists in me too. No, I usually just print one and copy them. Yeah, but the blue printer was giving you double-sided when the copier gave you double-sided. You would have had to go in and choose that. Oh, nice, interesting. Really? I wonder if it fixed one of my previous jobs and printed it as well. But I had like 4. I bet there's 3 more. I saw Jan in there on Friday, and I didn't talk to her because she looked like she was learning. You're off by a card. This is 1, 2, 3. It should be 1, 2, 3, 4. But otherwise, they're both up, which is good. Yeah, even look here, we've got up axial in green and then up. If it's up, then it's up. Blue is up. Okay. Feel free to collaborate. Okay, wedge runs up. No wedges or dashes on in pairs. I'm gonna actually point that out because I always forget, and then I see them, and we've got that assumed perspective part. So a reminder, assumed perspective here means that we don't ever add wedges or dashes. We know what we're showing. So when you see, wedged groups on the chair, you do not put wedges or dashes onto the bond line structure. It's assumed already. You have to know it. And actually it clutters things, and it makes things a little bit harder to read if you add it in. So no wedges and dashes on the chair. Deal? Deal. What is the up position on a down carbon? Look at the board for an example. I've got a down carbon on the right. What is the up position? Is it axial or equatorial? You're going to stay on the same carbon, yeah? But draw an equatorial. Yes. That is perfect. Notice how it looks here. That's basically what you're going for. What you had before was not this either. It was straight up. It just needs to be off to a bit. If it helps you, Andy, draw in the down axial group. And that will confirm for you that you're looking at the up equatorial. You know what I mean? Can I show you? So this carbon has a down axial. And now that really looks like an up equatorial ET. Beautiful. Great. Great. Can I give you some tips on your ET? Up, up. That's great. But now this is a down carbon, so the up group is up equatorial. The down group is down axial. You've got this drawn as if it's an up axial, but it doesn't exist on that carbon. So I erase this line. Start by drawing a down axial group, and then draw the equatorial group. Okay. Or you could take a hint from Melissa and just pick easier carbons. The carbons that are on the corners are often easier to show their groups on. Okay. This is a up carbon or down carbon? Down carbons have down axial or down equatorial? No. That's true. That is down axial. It's a down carbon, so it still has a correct. But here, is it really a down terbutyl group? It's up. So on a down carbon, an up group takes what position? Down axial or up equatorial? You've got an up group, which means it's going to have two positions in the two chairs. Up axial and up equatorial. On a down carbon, does it take up axial or up equatorial? Correct. I'm sorry. Down carbons have down axial and up equatorial. Where does the up group go? Up equatorial. There's no chance for it to be. You don't draw it straight up there. You just draw it up equatorial. Kind of, but this is down equatorial. We want it to be up equatorial. So instead of having it come this way, it should actually come this way. And then it needs to switch. So you go from an up carbon to an up carbon. You just drew it. You can't draw ET on this carbon anymore. You need to draw on this one or this one. Okay. No mention attachments yet. I want. Are you still working on that? Oh, that's okay. I want you to show me which groups are up, which groups are down. And remember, up groups always move between up axial and equatorial, but they're always up with wedge. Down groups are always down with dash. If you see a group that's ever up axial, it will also be up equatorial in the other one, and that's always a wedged group. If you see a group that's down or down axial or down equatorial, it's always dash. Yeah? Mm-hmm. Yeah. No, not on here. Does not matter. Well, actually, there you don't get a choice. Let's say that this is an up carbon. Well, here's an up carbon. Okay. 1, 2, 3, 4. 1, 2, 3, 4. I don't have a choice. 1 is up, 4 is down. If 1 is down, 4 is up. There I don't have a choice, but where you start, arbitrary. And then on your other chair, just change it. Up carbon, correct? That's right.
I don't know, so.
And this is a down carbon, correct? This carbon, is it one of our three up carbons? Or is it one of our three down carbons? This one here. Is it oriented up in space, or is it oriented down in space?
So honestly.
Let me grab my model quick. Can I borrow this, Yvonne? Thank you. So here's our cyclohexane. Do you see how three of them are pointing straight up?
Yeah.
And their vertices are literally pointing up towards them. Those we call up carbons. Up, up,
Yeah,
up.
but like.
So this carbon here, who cares about the stuff you do? Is that carbon?
Oh, I see what you're talking about.
I was like, why too?
So I
This is
Good. Up carbons have two groups,
So.
up axial
So here.
and down axial. And these groups here, we can describe them as up if they're wedged, and down if they're down. How would we describe these two groups? Good. They're both up. Now you want to draw terbutyl.
Yeah, what does that mean?
Carbon.
Oh, I see. Okay, I see what's going on here. Okay.
So terbutyl should be drawn straight.
Yeah, I
You can tell.
Good. Good. Now the ethyl group also needs to
I
change.
think it's this nut needs to be out, right?
Correct. Up, additorial. Good. No, that's it. That's great.
Is that it?
Yep, good work. Beautiful.
Okay, cool. I get it.
Perfect. Now in the chair flip, they'll both stay up. But this will go from axial to equatorial like this is, and this will go from equatorial to axial like that is. But terbutyl can no longer be on this carbon. The up carbon will flip into one of these two down carbons. All right. So Andy, I think you're ready to circle the most stable conformation. Yes, yes, this is great. This looks great. Good job. Yes, and you know why yours looks different? Just because you went a different rotation. Like this. That's exactly why I gave you this. Do you see how different these look from each other? That's just how different those two look from each other. It's absolutely correct. It is correct. You know what? It's almost correct. Your ether goes to your aldehyde counterclockwise. But here, your ether goes to your aldehyde clockwise. So they're actually mirror images of each other. Your aldehyde should actually be here. Mm-hmm. Yours is right. Well, not, I mean, unless there's a down group there, right? Like here. You can put it anywhere you want to. Anywhere you want. If an up group is on an up carbon, then it's up axial. If an up group is on a down carbon, then it's up equatorial. Mm-hmm. You got it. All right, I want to give you guys a break. Do you want me to go through this first and then give you a break, or do you want to give a break now and then go through it after before we transition into the next section? All right. So, I know not all of you got through all of it. Here's one thing that I would encourage you to do is to come back to it later. After you feel like you've learned all you can learn, and try to do it again from memory. Or not from memory, but apply it, rather. Okay, so here, what we're showing is an up group and a down group. And we've picked them to start on an up carbon and a down carbon. So remember, up carbons have up axial and down equatorial. So my up group on an up carbon is up equatorial. My down group on a down carbon is, I said that wrong, didn't I? Thank you. Up axial. Down group on a down carbon, down axial. When I do a chair flip, my up carbon will move to a down carbon or a down carbon on the other side. I have two options for this up carbon. My down carbon moves to the down carbon in the same direction, either way. Deal? So down axial becomes down equatorial. You can tell the difference because this one's off to a slight angle. But I can also prove it by drawing in this hydrogen that is up axial on that carbon. So it kind of verifies what I'm looking at. And then here's my up equatorial OH and my down axial H. Here is my up equatorial OH, and behind this is my down axial hydrogen. And then here's my down equatorial OH and my up axial H got in the way of my other OH. Some of you down here and down here might have drawn the exact same conformation just from as different of perspectives as these two. These are exactly the same conformation. It just depends on how you took the first chair and rotated the groups. Sound okay? Here, I have a 1-4 positioning. So I can choose either this pair, or this pair, or this pair to put my carbons on. These pairs are not equal to each other. These two dots in the middle, they are the hardest positions to draw the groups on. But these corners are much, much easier. So I'm going to show you both. I'll start with the corners. I'll put ethyl here. That's an up carbon. Where does my up ethyl go? Up axial. And here's an up tert butyl. Here's position 4. Where does up tert butyl go? Up equatorial. And then these other two positions are the hydrogens. Now you can kind of see how if you put your face here, these two groups are both pointing up at you, which is why they both get the wedge. But now I'll rotate. And to be fair, I could rotate them both clockwise so that I use these nice corner pieces again. But for your sake, I'm going to rotate counterclockwise, and I'm going to use these more challenging internal positions. Up ethyl becomes up equatorial on a down carbon. So it needs to have that slight angle. A lot of you are drawing a straight up to that ethyl, which indicates you're saying up axial on a down carbon. That's not a position. Tert butyl rotates the same direction. Now it's here in the middle. goes from up equatorial to up axial with a down equatorial hydrogen. If those hydrogens cause you pain, you don't have to draw them, but I believe, that those hydrogens can help clarify the positions that you've drawn to make them seem easier to interpret. Now let's take a step back. Which of these two chair conformations was the lowest in energy? Which of them has minimum axial groups? Raise your hand if you think the structure on the left is lowest energy or the structure on the right. Oh, not a lot of people raised their hands though. So what's the holdup? Andy, what do you think? Structure on the right? Why? How many axial groups? Oh, 0. Because we're not considering the hydrogens to be sterically strained groups. Just the OHs. How many axial groups here? 2 versus 0. This is the lower energy form. How many axial groups in our second set? How many axial groups here? How many axial groups here? And some of you might be feeling like my axial group there is not very axial. I don't know if I even straightened it out more. But again, remember, that's in comparison to this down equatorial hydrogen. So they both have one axial group. They both have one equatorial group. Which of them is higher strain? Or sorry, which of them is lower energy? Higher strain, we're circling the lower energy. Ethyl being axial causes less strain than butyl being axial. All right, now I think this is where most of you were getting to. We need to start by doing a rotation. Whichever way you rotate all of them the same. Actually, it doesn't matter which way you rotate, you're always going to have one of them on one of these internal. So I'm going to rotate clockwise. That wasn't clockwise. I'm going to rotate counterclockwise. So my chlorine is going to come down to the left. Is that an up chlorine or down chlorine? If it's up, then it's up. It stays up, and it becomes an up equatorial. Do you know what the CHO group is? Functional group? Aldehyde. Carboxylic acid's got that extra O. CHO is how we can abbreviate an aldehyde. That shifts to the back position. That's up. That takes an up equatorial position relative to the down axial hydrogen. And then I've got OCH3, up equatorial, moves to an up axial OCH3 with a down equatorial H. But you could have also drawn it the other way, where you rotate each of them to the right one. Now translating them, how many are wedges? Kira? All 3 are wedges, because we said a wedge is an up group, and they're all up groups. So here's the most important part. When translating it from chair to top down, I need to make sure that I keep my carbons in the same relative positions. So again, counterclockwise, it goes 1, 2, skip a few, 4. I need to make sure that they have that same relative position counterclockwise. That's the only way that I can get the actual structure. So I have a wedged OCH3. Next to that, I have a wedged CHO. Skip 1, I have a wedged Cl. Did I mean to put so many wedges on this? No. But I guess That's just my instinct, is to do a lot of wedges. I've only got one dashed group on this molecule. Which of these is the lower energy? The one on the right? Why? This has one axial group versus two equatorial. This has two axial groups and one equatorial. Minimize axial groups, maximize equatorial to maximize stability. All right, why don't you guys take a break? 6:25, we'll try to come back in and move into our new content.
Can you go over to going up versus down again?
Yes.
Like, because it's not just like goes down.
No,
Yeah,
correct.
Yeah, because it's like so what,
Well, look at the bond line. Anywhere the bond line is pointing up is an up carbon.
Okay, so there.
Yes. Anywhere the bond line is pointing down, it's a down carbon. And then notice how they alternate.
Yeah.
1, 3, 5, 2, 4, 6. Good. That's good. Yeah, yeah. And again, Elliot, which of these carbons is an up carbon?
We don't know.
None of them. All of them. You don't know until you start
Yeah.
drawing it. Yeah, yeah. I haven't had a single sip of this. I know.
What?
I'm just kidding. No. No. Not enough. Not enough information. You don't think so? It's not enough information. How did you lose the wedge and dash character? Where did it go? How does it transfer? Yes. Mm. Mm. Not a boat. You call it a boat? It's not a boat is a six-membered ring. That's a good question. A boat is a six-membered ring that does kind of do that, yes. But this is just a linear structure rather than a chair. Stays in the group, right? If it's up, that's Cardi B. It's up and it's up. Mm-hmm. Not what they're on, but how they're described. Because the carbons themselves will change. The up carbon will transition to a down carbon. But the group that is up will stay up. The group that is down will stay down. But it will change its relative position from axial to equatorial. Mm-hmm. So you've got that up equatorial becomes an up axial. Good.
Yeah.
Good. You got it. Amine? Yeah, it can be. Not for our class. You won't have to name it for our class. The PLO. So actually, they do tell you that whole worksheet is alkane based. So they tell you name everything as a substituted alkane, which means the suffix will always be a. You're gonna call it hydroxyl or hydroxy. Correct. Correct. And there's a benzene too. Yeah. And I've seen a lot of people that submit it and say ethylbenzene, which is a great way to name it. But for this exercise, it wants you to name it as one phenyl ethane. So when it comes to Yes. The problems that you've seen on active so far, just alkanes and alkyl halides, that's what you're going to see on the unit test. You're not going to have to name alcohols or alkenes or alkynes until later in the semester. And we'll revisit it. You know, at the U, they don't teach nomenclature. Really? No. They say this is easy enough for you to figure it out on your own. So you will be tested on it, but we will not teach it in class.
I was doing great, and then I was like, oh, not right.
Yeah, and they're like, yeah, you'll figure it out. And yeah, like you will, but there's not a good resource out there for figuring it out. But my approach is the exact opposite, where I say, you may never take another chemistry class again. And yet, I can explain to you the names of so many drugs that you'll come across just by pointing out that functional groups change the suffix of a word. So when you hear testosterone, I want you to think there's probably a ketone in that molecule, because there is. Or progesterol. I wonder if there's an alcohol in there. There is. Propofol has an alcohol. So I don't like to just like tease and play around until we get there.
Yeah.
I really like to show, yes, we have this naming system, but we're going to take it in increments as we get tested. Alkanes first with alkyl halides. Then we'll move to alkenes, then alkynes.
So for now, think of everything as alkanes and name the substituents instead of changing the suffix to all
Correct.
or whatever.
For that PLO, you will never have to change the suffix from ane. In fact, if you change the suffix from ane, you're technically doing it wrong. And by the way, this is still available. You can still turn this in. I'm going to change the due date eventually. The reason I wanted it due already was because we already covered nomenclature. So I want you to be applying it as we're learning it. But the problems you see on here are not reflective of the problems you'll see on the unit tests or the exams, because this was not made by me, but it is required. And I think I have like 12 submitted already. So we're just 11. So we're just looking for like 15 more from you guys. I think there's almost 30 of you. All right. Do we have any remaining questions on chairs before we move on? Okay. Then this gets us into section 5, which is on stereochemistry. We've been talking about stereochemistry in terms of Newman projections, chair conformations, and wedges and dashes, all stereochemistry. So now in section 5, we're looking at the tetrahedral carbon and how this gives us chiral centers. Chiral is a Latin word. Does anybody remember what it means from your reading? Latin doesn't mean mirror. I'm sorry, chiral doesn't mean mirror in Latin, but it has something to do with mirroredness. But chiral itself is a Latin word for, not center, not tree, hands. Hand is chiral, or handedness is chiral. So when you think about chiral centers, your hands are the best tool for you. Tell me about your hands. Are they symmetric in and of themselves? Can't I cut it like this and reflect, the front half of the fingers to the back half? Why not? Well, that would be splitting it like this. My thumb and my pinky are very different. But what if I split it like this? Are my knuckles and my palm the same? No, my knuckles and my palm are not the same. And then tell me about your two hands. Are they symmetric to each other? they're mirror images, you know, plus or minus a few freckles. But can you superimpose your hands? Meaning get everything to line up. If you get your palms facing the same way, you get your turtle. Your thumbs do not line up. If you get your thumbs to line up, your palms and your knuckles do not line up, correct? So your hands represent chirality, handedness, in that they are non-superimposable mirror images. Can you name something that doesn't have a mirror image? No. You can't. Everything has a mirror image, even if its mirror image has not been taken. Our Milky Way has a mirror image, even if that mirror image doesn't exist and there's not a mirror large enough to reflect it. Everything has a mirror image. Can you think of something that is superimposable with its mirror image? What do you have, Will?
She said it first.
Andy? A circle?
I'm not taking credit for it.
So, to be fair, yes, a circle is superimposable with its mirror image. We could expand that too and say that maybe like a bouncy ball that's uniform in its color and everything is superimposable with its mirror image. Elliot, did you have another? Spherical thing. Sorry? A cube also works, yeah. I mean, if you want to stay in the context of chemistry, your s orbital, but also your p orbital is superimposable with its mirror image. A car, superimposable or non-superimposable with its mirror image? No, you take the mirror image of an American car and you get a British car. The sides that the steering wheel is on have flipped. What about you? If you needed to get a heart transplant, could you take the heart from a mirror image universe? You guys know Doctor Strange? Reach in there and take out that mirror image heart, transplant it with your own. Does it work? Because your heart is non-superimposable with its mirror image. We call those things that are non-superimposable with their mirror image chiral, because they have the same property that your hands have. They are non-superimposable with their mirror image. So chirality centers are tetrahedral carbons. We can say sp3 carbons. And here's the requirement for these. They have 4 distinct groups. In that 3-dimensional space, all 4 things that it's bonded to are different from each other. What that means is that it lacks a plane of internal symmetry. Just like your hand lacks an internal plane of symmetry. You cannot reflect thumb and pinky. You cannot reflect, what do you call this? The heel of your hand to your fingertips. You cannot reflect your knuckles to your palm. There is no plane of symmetry in your hand. Chiral centers lack a plane of symmetry because they're bonded to 4 different things. And those chiral centers have 2 configurations. We've just finished talking about conformations, but here we're talking about configurations. Conformations can rotate between each other. Configurations are just describing how things are configured. And most chiral things do have 2 configurations. Which hand is on the board right now? My left hand or my right hand? Tell me the absolute configuration of my hand. Alyssa? You just think it's my left hand because you saw me draw it, my left hand up there. Is it really my left hand? When my right hand can fit in it perfectly? Which one is it? Or is there not enough information? We know it's a hand, and literally by the use of the word, we know that it's chiral, because that means hand. Business. So which chiral thing is it? My left hand or my right hand? This is the issue with absolute configurations. Here is a Cl group. Now, looking at the 4 carbons in this molecule, these 3 carbons we describe as achiral. Achiral things lack this property of chirality. And chirality is the lack of symmetry. So we can call chiral centers asymmetric centers, and we can call carbons that have a plane of symmetry achiral carbons. They're symmetric carbons, which means they lack chirality, so they are called achiral. That's how important this lack of symmetry is in chemistry. Lacking symmetry gets its own name. Lacking the lack of symmetry, having symmetry, gets called achiral. And how can we say that these are all achiral? Well, they don't have 4 distinct groups. CH3, CH2, CH3. They all have at least 2 hydrogens, not 4 distinct groups. But what about this carbon here? This is a chiral carbon, an asymmetric carbon. But it's not bonded to 4 different atoms. It's not bonded to 4 different elements, rather. 2 of the elements it's bonded to are the same. They're both carbon. But a primary CH3 group is distinct from a secondary ethyl group. Those are 2 different groups. They don't reflect into each other. A CH3 is not a CH2CH3. Correct? The chiral center needs to have 4 different groups. No matter how far down a chain you need to go to find a difference between them. But if there is never a difference, it's not a chiral center. And then, of course, it has the hydrogen and the chlorine. Those are its 4 groups. But what configuration does this carbon have? There's not enough information. You cannot say that this chiral center has one configuration or the other because you don't know anything about how those 4 groups are arranged in space. You cannot say what hand this is because you do not know how they're arranged in space. What is one piece of information that you need on this hand before you can decide its configuration? What would give it away? Fingernails would give it away. What else? Knuckles would give it away. Anything else?
Your palm lines.
Yeah. Bring it to a psychic, she'd tell you your future. That would give it away. Your fingerprints would give it away. Or if you had a nice big wedding ring on here, that might not as easily give it away, actually, because some people wear jewelry on both hands. But the knuckles, the fingernails, that for sure gives it away. But does it give it away without any proof? Like, how could you prove it systematically that it's your left hand? You'd have to say, first, put your palm away from me. Then, when the rotation from your thumb to your pinky is counterclockwise, it's your left hand. And if your palm is away and rotation from thumb to pinky is clockwise, then it's your right hand. So we need to first orient the structure in space, and then just have a rule. When you rotate this way, it's this configuration. When you rotate this way, it's another configuration. So we call these, for chiral carbons, the Ingold Prelog rules. None of them have meaning. They're all just names. And here's what the rules say. At a chiral center, 1, rank groups by highest atomic mass at first point of difference. Meaning if two groups have the same atomic mass, they cancel each other out. You move on to the next group. Highest mass gets priority number 1. Lowest mass gets priority number, how far does it go? There's just 4 groups. So the lowest group is priority 4. The second rule is with priority 4 placed away, meaning dashed. It's pointed away from you. It's not in plane, it's not coming towards you. That's like what we're saying here. With my palm facing away, orient your chiral carbon in space. 3, determine rotation from 1 to 2 to 3. Notice which number is not in that list. 4. We already took care of 4 because we put it away. How come I didn't mention rotation? I said from thumb to pinky, and I never mentioned the palm because we already oriented with the palm. We oriented with lowest priority. Now rotate from 1 to 2 to 3. If the rotation is clockwise, I've drawn it like this for a reason. If the rotation is clockwise, then this makes up the top half of an R. And we label that configuration R, like saying right-handed, R. I'm sorry, we don't get to pick the letters. If the rotation is counterclockwise, then this makes up the top half of an S. And we call that rotation, we call that configuration S. So, we had this chiral carbon. And we decided that this does not have enough information to be R or S. Because we don't know how that lowest priority group is facing. We don't know if it's in plane, if it's towards us or away from us. We cannot determine R or S. That means that there are 2 other ways to draw this structure. One where the chlorine is coming towards you, and one where the chlorine is going away. To be fair, we could have picked any number of those groups, but it's just much more common to have the bond line zigzag, and so let's keep those in plane. Here's my chiral carbon. How do I rank these groups? We can actually sketch this out if it helps. It doesn't always help, so just pay attention to see if it does. Well, I've got a chlorine and a hydrogen and then a carbon on either side. So I can rank priority number 1 pretty easily, and I can rank priority number 4 pretty easily. But priority 2 and 3 is not as easy. Since that carbon in each group is the same atomic mass, I need to go to the next atom in the group. To the left, my next atom is just a hydrogen, and to my right, the next atom with the highest atomic mass is a carbon. So I'm actually comparing hydrogen to carbon here. Which one is higher priority? Carbon. Which one gets priority number 2? Carbon. So this whole group gets priority 2. This whole group gets priority 3. The first point of difference was at the second atom in the chain. So priority 1, priority 2, priority 3, priority 4 is actually coming towards us, which means that our rule number 2 is broken. I cannot determine the absolute configuration of this molecule. So we can take advantage of something we learned in Newman projections. That exercise that I had you guys do with the structures, rotating them one bit at a time. We can try to rotate this from zigzag to zig-zig. And I can get this chlorine to rotate through. Notice this should be what you guys have on your paper at the bottom. You've got this dashed chlorine. We're rotating it from zigzag conformation to zig-zig. What happens to the position of the chlorine? If it's rotating, if it's pointing away from you and you rotate it like this, now it's rotating, now it's pointing towards you. This is what I wanted you guys to fill in on that graphic, is that this becomes a wedge. Priority 1, priority 2, priority 3, with the lowest priority 4 pointing backwards. So now I can say that this is 1 to 2 to 3 counterclockwise. This is an S absolute configuration. What does that make this structure? Must be R, because it is configured differently. The chlorine is not going back, the chlorine is coming forward. If you scooted these two structures over, would they superimpose? No, they're non-superimposable mirror images. That chiral carbon is oriented different. So we should find that this has absolute configuration R. Here's priority 1, 2, 3. That's R. So there is a trick. Rather than needing to rotate your structure so that you get the lowest priority and back, we can actually use this tip. If your lowest priority is forward, if you have a wedged group that is your lowest priority, then you can determine the rotation from 1 to 2 to 3 and just assign opposite of what it appears to be. We'll pick up with that on Wednesday in class. I've got the same rotation, 1 to 2 to 3, 1 to 2 to 3, they're both counterclockwise. Well, if I can just recognize that this group is oriented the wrong way, then I can assign it counterclockwise and realize I'm looking at it wrong. When we come in on Wednesday, I'm actually going to talk about how clocks are a good analogy for this. So I kind of want to tease you. Think about the direction a clock sees as clockwise. And then come back on Wednesday and we'll talk about that. Have a good night. Get home safe.